So thank you very much. I want to thank Matt and Hugh very much for inviting me and for giving me the opportunity to talk. I think it's really extraordinary that they are that supportive also towards young researchers. And no, that's something out of the ordinary, so not something that I could have expected. Maybe that's because they believe in the block universe, so they know that my future accomplishments are just as real as the past accomplishments.
We know that you are going to be an old researcher.
So I'm going to start my talk for the same point as many others. What was called the most profound discovery of science, that nature is non-local. And this quote is from Stubb, who incidentally was also one of the first people who kind of thought about retrocausal accounts of this fact. There's one little caveat that I should make, that maybe the only person here that can dispute this claim is Lev. But other than that, the issue is settled by all reasonable means, and I really admire people like Johansson or Travis Norson who have the patience to respond even to the unreasonable objections. But I think the question today is not if the principle of local causality is violated, but how and what that means for us as we move forward towards new physics. So here's a quote from John Bell, to whom we owe, of course, Bell's theorem and this insight into the non-locality of nature, who said, "For me then, this is the real problem with quantum theory, the apparently essential conflict between any sharp formulation and fundamental relativity. That is to say, we have an apparent incompatibility at the deepest level between two fundamental pillars of contemporary theory. It may be that the real synthesis of quantum and relativity theories requires not just technical developments, but radical conceptual renewal." And the first part of my talk is to clarify some of the words he's using here. So what does he mean by the conflict between relativity and quantum theory? What does it mean by sharp formulations of quantum theory? And why is this conflict an apparent one only? And then, of course, the second part is what could be the radical conceptual renewal that is necessary to bring relativity and quantum non-locality into peaceful coexistence. And I think I'm not giving away too much when I'm saying that retrocausation could be one of those possibilities. So what is the conflict between relativity and non-locality? So initially, it was believed that it must be the threat of superluminal signaling, right? But it's now well understood that this is not the essential problem, and it's well established by various no-signaling theorems in quantum mechanics that a violation of Bell locality does not imply the possibility of faster-than-light communication or any other way to violate relativity in an operational manner. So the conflict is really more subtle than that. The conflict is that according to the most common reading of what the violation of Bell's inequality means, it is saying that there must be some sort of instantaneous influence between space-like separated events, where I'm losing influence in the most general sense of the word. And relativistic space-time, having no structure of absolute simultaneity, is just not very hospitable to those kinds of instantaneous influences. So it's not clear how to formulate a physical law that is able to account for violations of Bell's inequality and thus for non-local correlations, because we know that no local theory can account for those. So this is basically the structure of Newtonian space-time, where you have the structure of absolute simultaneity, and in relativistic space-time you do not have that structure anymore. The structure of relativistic space-time is the structure of light cones. So it's not clear how to implement instantaneous influences between distant events in relativistic space-time. So the second question is, what does Bell mean by sharp formulations of quantum theory? And I think he doesn't really give that list explicitly, but I would say that these are more or less his requirements. The first is that this quantum theory should not be plagued by the measurement problem. And the measurement problem is really just a euphemism. You know, a theory that has a measurement problem is just logically inconsistent. So this requirement not being plagued by the measurement problem is just a requirement for being a logically consistent theory. The second is that there's no observer in this theory. That is, observer or observation or measurement should play no fundamental role in this theory. There are, of course, measurements in those theories, and there is an observer in these theories, but they are part of the physical description. They're not somehow outside the physical laws, as in the Copenhagen interpretation, and they play no fundamental, so measurement or observation is not a fundamental or distinguished notion in those theories. And the third and most important one is that the theories must have a clear physical ontology. It must be clear what these theories are talking about, right? What are the fundamental physical entities that those theories postulate, that are the objects of their physical descriptions, and how do certain terms in the mathematical formalism of this theory refer to those entities that exist supposedly in space and time. So, to use another terminology of Bell's, there should be a theory of beables, not a theory that is fundamentally about observables. And I'm very much convinced that if you want to have an informative discussion about any of the issues that we were discussing here, we need to know what we are talking about. We need to know what our theories are talking about, what the ontology actually is. Like Bell gives a nice example to illustrate this, by asking what is it actually that cannot go faster than light, right? This was like the minimal consensus that everyone talking about non-locality and faster than light signaling also had, that nothing should go faster than light. But what shouldn't go faster than light? What is the actual physical stuff that isn't supposed to propagate with superluminal speed, right? Measurements don't propagate, they're always local. For instance, most people have the intuition that in a relativistic theory, the support of the wave function shouldn't spread faster than with the speed of light. But this intuition, I believe, should actually be grounded in a certain understanding of what this wave function is or represents. For instance, if you believe that support of the wave function shouldn't spread faster than with the speed of light because particles cannot go faster than the speed of light, then the theory should have an actual moving particle and should tell you what the motion of this particle has to do with the spreading of the wave function. Another good example, I thought, was in first day our discussion of weak measurements. If you want to know if there's any sort of retrocausation manifested in weak measurements or weak values, you cannot read that off of the probabilistic, of the formalism. You need to have a theory that actually describes these measurements, or at least tells you, or maybe in the best case tells you what they are in fact a measurement of. Or a third example, I thought, was our discussion of time reversal symmetry this morning, right? The question being, what is it actually that should remain invariant under time reversal if the theory is supposed to be time reversal, right? Probabilities is maybe not the best candidate, or at least it's not an obvious candidate, at least as long as you are not able to say what is actually changing in the world when the probability of an event is changing. So these are, I think, all questions that need to be answered in terms of a physical ontology. And there are basically three candidates of a sharp formulation of quantum mechanics in this sense of Bell. The first being Bamiyan mechanics, the second being the GRW theory, or other collapse theories, and the third being the many worlds theories. So, what are the ontologies of these theories? Bamiyan mechanics is a theory about particles. So, the Bamiyan actually believes that there are atoms that are elementary particles, and that these particles have an actual position in space, an actual configuration in space, independent of whether you measure them or not. And if you believe that, it's relatively straightforward to formulate the Bamiyan guiding equation, the law of motion for these particles, which is an explicitly non-local law of motion, thus accounting for violation of Bell's inequality and quantum non-locality. And then a statistical analysis of this theory reproduces the quantum formalism. So, in particular, Bamiyans usually want to stress Bamiyan mechanics is not an interpretation of anything. It's a theory that you analyze and then you recover the statistical predictions of quantum mechanics. So it's, so to speak, the missing ground floor for the top floor, which is the quantum formalism, to pick up this picture that we had earlier today. I also wanted to say that you can then prove in Bamiyan mechanics that the theory is non-signaling for typical initial conditions. That is, for all initial conditions of the universe except for a set whose measure is very close to zero. Because many people said that these theories require fine-tuning to avoid faster than light communications, and in this sense it's actually the opposite of fine-tuning. It's actually typical initial conditions. So for almost all initial conditions you can prove that the theory is non-signaling. So the GRW theories, they change Schrödinger's equation, right, by introducing an objective collapse. And well, these theories can also be provided as a physical ontologies. Not all people who do the GRW agree with this program of having a primitive ontology. In the theory, the G in GRW does, and the R in W, they don't so much. But the point is that, of course, the collapse in GRW theories gets rid of superpositions, but there's still a difference between, let's say, the wave function of this table in physical space. So you want something which actually corresponds to this table in physical space. Actually, the primitive ontology in space and time, right, that is posed as the fundamental constituents of matter. And there are two possibilities for that, which are discussed in the literature. The first is to define from the wave function a mass density in three-dimensional physical space. And the second is what Tomulka called flashes, but it's actually going back to a proposal of Bell's, which is that there are those random, where the wave function determines a probability distribution for these random flashes, right? Those are just random flashes of matter, right, that appear in three-dimensional physical space. And unlike in Bamiyan mechanics, where you have a continuous trajectory, right, those flashes are not enduring entities, right? They are just different flashes as a decoration of space-time. And he puts it so nicely, a macroscopic object then would correspond to a galaxy of these flashes. So, yeah. What's also interesting is that actually of those three alternatives, the GRW theories are the only one that are intrinsically random, which is a bit ironic, because intrinsic randomness often believed to be, one of the fundamental things about quantum mechanics, whereas GRW theories are actually not quantum mechanics in that they change they give up unitarity and they change the Schrödinger equation and they make predictions that differ from those of standard quantum mechanics and will hopefully be testable at some point. So the third option is for serious quantum theory is the many worlds theory, and also not all advocates of many worlds adhere to this program of having a physical ontology, but those who do, there are also different proposals, some of which also insist on local beables in three-dimensional space and time, but those who are more pure Averetians and want to have only the wave function, then the program would actually be to reify this universal wave function or universal quantum state. So this would actually be a beable. Quantum mechanics would be about the universal wave function, that would be, well, universal quantum state, that would be the fundamental physical entity, and the fundamental beable, although not a local one. And this has rather radical consequences. Aside from the obvious ones that you have many worlds, would mean sort of that the fundamental stage of physical reality is not three-dimensional physical space or four-dimensional space-time, but this extremely high-dimensional space that usually would be configuration space, but here it's not the configuration space of anything, because fundamentally there's only the wave function. And then you would have to tell some sort of story about how this abstract quantum state on this high-dimensional space actually corresponds or represents to stuff in three-dimensional physical space or four-dimensional space-time. Yeah, but I'm also leaving out, I guess, the many-worlds the many-worlds theory for the reason that this is the only one where you can have an actual disagreement about if and in what sense this theory is actually local. So this is, I guess, in this sense, the only caveat that I would make. I also wanted to say something about this notion of hidden variables because it came up a lot. So these theories are not actually hidden variables theories. So first, as Bell already pointed out, it's actually absurd to speak of the primitive ontology of this theory as hidden variables because it's precisely the thing that's not hidden. It's precisely the thing that's supposed to make connection with actual observation and with physical reality. So for instance, according to Bamiyan mechanics, we see this table here because it's actually made out of Bamiyan particles who are at this position. And we see the dot on the screen in the two-slit experiments because this is where the Bamiyan particle actually hits. And we see a pointer in the lab pointing to the left rather than the right because this pointer is constituted by Bamiyan particles who are actually moving to the left rather than to the right. Second, hidden variables used to mean something in quantum mechanics. It used to be the question whether the quantum observables and the quantum statistic could be reproduced by classical variables that are somehow hidden behind from direct observation but would somehow reproduce this quantum statistics. And we know that on a very reasonable assumption this is impossible, and this is not what these theories are trying to do. But quite the contrary, these theories, if you want, are anti-realist about the usual quantum observables. But they only try to, or they don't try, they actually do recover the predictions of quantum theory in terms of how the configuration of matter constituted by the primitive ontology, be it the particles or the mass density or the flashes, actually evolves, right? So there's nothing, a Bamiyan particle has nothing over and above a position in physical space, right? And then it's only if you analyze the theory for certain measurement-like situations that you recover the statistical predictions of quantum mechanics. Also, I wanted to show this picture because many of you are very fond of weak measurements, that you can actually see the Bamiyan trajectories in weak measurements, not in strong measurements. And this is actually a genuine prediction of Bamiyan mechanics, that if you do this sort of weak measurement, you will measure the Bamiyan velocity field. So this would be the Bamiyan trajectory for the double-slit experiment. Of course, in every run of the experiment, one particle moves along one single trajectory, and in a typical ensemble, you would recover this interference pattern. But let's come back to the Bell quote and discuss why this conflict is really only an apparent one. And one reason is that there are actually relativistic generalizations of any one of these what we call sharp formulations of quantum mechanics. So let me briefly review for you what can be done. So the problem in making Bamiyan mechanics relativistic is that you have this non-local law of motion, which is such that the velocity of one particle at a moment in time depends on the position of all the other particles at the same moment in time. So you need this sort of synchronization between the particles to write down the Bamiyan guiding equation, the Bamiyan law of motion. And again, in relativistic space-time, you do not have the structure of absolute simultaneity. So the easiest thing that you could do is actually give up this structure of relativistic space-time and introduce a foliation of space-time. And you can do this in a way where you can prove that this preferred frame, this foliation, is not empirically detectable. So I think in one of the announcements of the conference, there was this quote from Bell where he said that maybe the easiest way to reconcile quantum mechanics and relativity is just to return to the early days of relativity, where this was just a phenomenological thing, and this is basically what he was referring to. But for the obvious reasons, many people don't find that to be an attractive option, including me. A more recent work showed that even in Bamiyan mechanics you can actually do better. That is, you can actually have this foliation, right, that synchronizes the particle generated by a Lorentz invariant law, and even in such a way that the foliation comes out of the universal wave function. So the universal wave function determines this foliation of space-time in a Lorentz invariant manner. So a Lorentz invariant manner. So this formulation, would actually be perfectly Lorentz invariant. And strictly speaking, you would not add an extra structure to space-time, although you would have this extra dynamical structure that comes out of the universal wave function. So this is one possibility. And this formulation is seriously Lorentz invariant. One can debate whether it's seriously relativistic. It still has this air about it that you are adding some extra structure. Even if it's not empirically detectable, even if it's not really an extra structure in space-time, there is this preferred frame, after all, where the particles are synchronized. The GRW collapse theories seem to lend themselves more to a relativistic generalization. So the first result was relativistic GRW with the Flash ontology by Ordi Tomolka in 2006, and the more recent result by Bedingham and collaborators. Fortunately, I think he's not here today, but that's a pretty nice result for the mass density. And just briefly spoken, you have in GRW this intrinsically stochastic law, and again, basically the universal wave function, or the wave function of the system, has what it does is to coordinate these random events in space-time and correlate these random events in space-time, and it can do so in a Lorentz invariant fashion. So, and it's an interesting kind of randomness, actually. It's a kind of randomness that cannot be simulated by just throwing dice in the past, right? By just generating random numbers in the past. But the dice are thrown, so to speak, at the actual events where the localization, for instance, of the flashes takes place, but again in a coordinated manner, coordinated again by the wave function, but again in a Lorentz invariant fashion. So this can be done, but there are other prices to pay. For instance, of course, you have a more contrived law, you have less natural ontology, you have additional parameters, you have actually a relatively weird kind of non-locality, because you actually have, at least with a mass density, a spontaneous delocalization and localization of matter. So there's also obviously a heavy price to pay here. So now we're coming to another possibility, which is not, it's not worked out in an equally detailed fashion, but another logical possibility is to have, time-symmetric relativistic interactions at long past and future light cones. So, in other words, retrocausation. And it's not a neglected route here among this audience, but as you know, it is a neglected route in general. And obviously, the benefit here would be that you could account for non-local correlations by drawing exclusively really on the structure of relativistic space-time, right? With particles or whatever local beables you have interacting along their past and future light cones. And I just studied a simple toy model to see, to get an intuition and to see in what sense you can actually get non-local correlations from such a model. And it was, of course, heavily inspired by Hugh Price's book that I read 2 or 3 years ago, and also by our study of Wheeler-Feynman electrodynamics. And it's really a simple toy model. It's not as sophisticated as what Ken Wharton is doing. It doesn't even look very quantum, but I think it's pretty neat as an intuition pump for what can be done. So the toy model is defined by the following assumption. So you have actually particles moving through relativistic space-time, and they have an internal degree of freedom, which we call spin, but which is represented just by a vector in three-dimensional space pointing in one direction. So as I emphasized that these primitive ontology formulations of quantum mechanics are not hidden variables theories, this is an actual hidden variable in the original sense. So I'm not thinking that this is something too serious for a fundamental theory of nature, but it's useful for this particular toy model. So we will consider an ensemble of pairs of particles whose initial hidden spin is randomly distributed over the two-sphere, but in opposed directions, right? So one is starting with particle A starting with S0 and particle B is starting with minus S0, where S0 is just randomly distributed over the sphere. Then I'm assuming that the spin measurement cannot determine the exact orientation of this internal spin vector, that's why it's a hidden variable, but only the orientation of S relative to the direction in which the spin measurement is being carried out, right? So, and the fourth assumption is that, as we learn from quantum mechanics, a measurement is not a purely passive process, but it will affect the state of the system that is being measured. And in this case, I'm assuming that it's affected in such a way that this internal spin degree of freedom is projected into the direction in which it's being measured. So if that would be like the hidden spin of the particle, and I'm measuring spin in direction A, since this is pointing more towards A than so in the direction of A rather than minus A, the result of this measurement would be A spin up, right? And the spin of this particle would be polarized in the plus A direction. If this internal spin degree of freedom was pointing into the minus A direction, the result of the spin measurement would be A spin down, and this internal spin degree of freedom would be polarized in the minus A direction. And now I have to consider an interaction among these particles. And this interaction, right, since we observe in an EPR kind of experiment these anti-correlations between spin measurements in the same direction, so I'm assuming that these internal spins are repelling, so to speak, right? That the action of one particle on the other is such that it rotates or tilts this internal spin into the direction opposite to its own. So it looks somewhat like that. Okay? And I assume that this effect is manifested as an advanced and retarded action of one particle on the other. So if this is the trajectory of one particle and this is the trajectory of the other particle, particle A here will exhibit this effect on the other particle spin that I just described here, where it intersects the future light cone, and here where it intersects the past light cone. And I also have to assume, because we know that these correlations persist over very long distances, and if quantum mechanics is true over arbitrary long distances, that these effects are unattenuated by distance, so realizing sort of an entanglement. So, of course, in a more mature theory, you would want to have something that actually realizes the structure of entanglement. So, presumably something like a wave function, but this is really just a very simple toy model. So, it's really very difficult in general to write down a relativistic law that produces non-local correlations. Right here, it's very simple to write down a relativistic law for this simple toy model. Of course, I still have to show you that it produces non-local correlations, but it's relatively simple to write down this law. It's really just the particles are repelling, spin of the particles are repelling each other here in this fashion, where the actual spin configuration is evaluated at the retarded and the advanced time. So it's again this picture where the particles are interacting along past and future light cones. And here, if I take the second order law, I'll have to add some assumption about S dot as an initial condition, and to assume that S dot is of both particles is 0, at least on average. it's easier for the statistics to replace that by the first order law. But then this law is not actually time-symmetric in the sense of time reversal invariant. So, but it doesn't really matter what kind of interaction you take to realize this model, as long as these assumptions are satisfied. So the first thing we can look at, just as a point of reference, is the model without advanced interactions. Now we have actually a completely local model, really just by this hidden variable. And of course we now know that there's no possible probability distribution of this hidden variable S0 that will reproduce non-local correlations violating Bell's inequality. And indeed, for instance, for settings like this, 0, 120, 240 degrees, we look at the probabilities of the anti-coincidences. Or I should say, did I say that A is the result of spin measurement of particle A and B is the result of spin measurement of particle B, given this, the spins are measured in these directions, A and B, and we are interested in the statistics of the anti-coincidences. So we are looking just when A is not equal to B. And we see that we can easily see that this will sum up to 1. And the Bell inequality in its simplest form demands that this is greater or equal 1, so that Bell's inequality here is always satisfied. Though it's interesting to note for later that this case is already critical, so that we already have equality here in this inequality. But of course, in this without advanced interactions, this is just a local hidden variables model, exactly the kind of model that is excluded by Bell's theorem, and of course we see that Bell's inequality for this case is satisfied. So now we have to look what happens if we admit the advanced interactions, so these interactions at long future light cones as well as past light cones. And we can just make here a heuristic analysis of the situation in this simple toy model. And of course the catch now is that what happens here between the source and the measurements will also depend on the particle states post-measurement that have already been affected by this interaction with the measurement device. So the advanced action on particle A of particle A on particle B, right, in the past is such that this internal spin of particle B is tilted into the direction opposite to that of particle A's future measurement result. And in a similar fashion, the spin of particle A is tilted here in the past into the direction opposite to that of B's future measurement result. So I call that a feedforward because, so to speak, every particle gets a feedback of the measurement result of its partner. But then, the particle here that has received this feedforward so particle B that had received this feedforward of particles A's measurement result also has here an advanced interaction with particle A back in the past. Okay, and now since this particle has been tilted into the direction opposite to A's measurement outcome, A itself, right, this earlier copy of A, will be tilted into the direction, right, into which it's going to be measured in the future. So I've called this a pre-enforcement because it's, so to speak, a preemptive reinforcement of A's future measurement result. And this will, in a similar fashion, go on, but further down the word line, these effects coming from the future measurements are more and more diluted and they won't contribute much. And there is, of course, also always the retarded action of the earlier particles on the future, so reaching the partners in the future, but basically the effect of this particle, of this retarded effects is just to rotate the spin of the particle back into its original position. So this is, I don't know, we had a discussion about the terminology, so this is what I had in mind with a zigzag causality, because it's actually going like a zigzag. Well, so just from this heuristic analysis, we can tell that the final spin state, right, by the time of measurement, will be a convex superposition, so a convex combination of the original spin orientation, then B's future measurement result, right? And so this is the term coming from the feedforward, whose sign is opposite to that of B's future measurement result. And this is the term coming from the pre-enforcement, which is whose sign is the same as A's future measurement result. And a similar expression will describe the final spin state of particle B. And well, since in general feedforward will act only for a brief moment of time, and this pre-enforcement is just, so to speak, the echo of feedforwards, it's reasonable to assume that B is greater than beta is greater than gamma is smaller than alpha. So alpha is greater than beta is greater than gamma. So now we can just compute the outcome, so to speak, by projecting this final spin states into the respective directions into which the spin is being measured, here into the direction A and here into the direction B. Right? And every possible result corresponds to a valid evaluation of this equation. So now happens something interesting and remarkable. So if that was boring, this is the time to pay attention again, which is that you see that here the sign of the measurements appear, so the sign of this expression, that is the measurement results I and B, which are +1 or -1, appear on both sides of the equation. And there are actually cases, depending on the scalar product and the scalar product, where there is just a unique possible evaluation of this equation. But there are also cases in which different possible prescriptions of A and B will correspond to valid evaluations of this equation. Right? So where this initial state is 0 doesn't uniquely determine the measurement outcome. And in these cases, there's a sense in which you could say that the measurement outcomes are, so to speak, retrocausally responsible for their own occurrence, right? Because it's due to this pre-enforcement term and also due to this feedforward term, mostly due to the pre-enforcement term, that they come out the way they are. Okay, is this point clear? So keeping all the other relevant parameters fixed, the measurement outcomes could actually be different. So I dubbed this phenomenon as a self-fulfilling prophecy, because in this sense, as I said, you could say that the measurement results are responsible for their own occurrence. But there is actually a deeper rooted problem in here, which is not only just an artifact of my model, but it's actually a characteristic of theories admitting retrocausal influences. So the deeper rooted problem here is that you have no Cauchy data. So theories which allow for advanced interactions and retrocausations in general do not allow for Cauchy data. Cauchy data means that you have the specification of initial conditions at one moment in time, respectively one space-like hypersurface, and that's supposed to determine the complete history of the system. Right? This is Cauchy data, and in general you don't have that in theories that admit advanced influences. And this is a huge technical challenge. So the point here, to say the same thing in different words, is the underdetermination of the time evolution by initial data. And this is something, this Newtonian paradigm, so to speak, that you can just give initial data and then the laws of nature determine the entire history of the system, is very deeply rooted in physical thinking, even deeper, I would say, than philosophical ideas of presentism or so on. Because this idea, this Newtonian paradigm, has survived, in fact, even relativity. Right? Even special relativity and even general relativity, if you look at the Hamiltonian formalism, you have this idea of initial data and space-like geometry, spatial geometry, evolving according to a time parameter. Right? So it's this idea that you give initial data at one moment in time, and this determines your time evolution. And this is so deeply rooted in physical thinking also because these are the sort of equations that physicists are usually trained to solve. Right? They're usually trained to solve laws of motion that are given by differential equations, right? Ordinary ones or partial differential equations, and which reduce to initial value problems. And I want to give you another example where you have this problem of the underdetermination of the time evolution by initial data, which is Wheeler-Feynman electrodynamics. Right? It's this theory where you do not have electromagnetic fields, the particles interact directly, again this picture, along past and future light cones. And we have a serious mathematical problem with this theory, that we don't know almost nothing about the solution. We know very little about the solution theory. So about existence and uniqueness of solutions to these equations of motion. Right? That is, we do not know what sort of boundary conditions we have to specify to ensure existence and uniqueness of solutions. And because those are not the ordinary differential equations that physics and mathematics are trained to solve, they amount to so-called delay differential equations, plus here you have actually advanced terms. And there are very few people working on this problem, and most of them are from my group actually. But there is this proposal still, which is a possibility that Wheeler and Feynman they allude to, which is that in fact to get existence and uniqueness, to specify a unique solution of Wheeler-Feynman electrodynamics, you do not need to give initial data only on one space-like hypersurface, but on entire segments of trajectories. And this is a speculation. We don't know if that's the case mathematically, but if that was the case, it would be extremely interesting. In fact, I think that would give a much more severe blow to presentism than even relativity did, because then what defines the physical state, right, the minimal physical state that determines the time evolution of the system itself has a temporal extension, right? It's not this thing without temporal extension, so that would be extremely interesting. A second example, in fact, is the transactional interpretation of quantum mechanics, where of course the basic postulate is that you have advanced and retarded solutions of the quantum mechanical wave equation. But then the problem is, what determines the boundary condition for the advanced solutions? And basically this whole story that Kramer comes up with, the pseudo-time sequence and also the offer and confirmation waves, is really just a way to specify, given the initial state, that I can prepare what sort of advanced solution of the quantum wave equation actually will determine the outcome. And I don't think that the story that he gives works, but I feel like many discussions didn't really put the finger on the actual problem, which is that in such a theory you do not have advanced and retarded, you do not have an initial value problem, you do not have Cauchy data. And it's also very interesting, one example where you don't have this problem, which is Maxwell-Lorentz electrodynamics. And why? Because here you have, as additional degrees of freedom, the electromagnetic field, right? And so one interesting thing is that if you take the propagator, right, the potentials to be the difference between a solution where the propagator is purely retarded or purely advanced, or a mixture of both, right, is just the solution of the free field equation, right? But more interestingly, regardless of whether you take the propagator to be time-symmetric or purely advanced or purely retarded, you do have Cauchy data because you have the electromagnetic field as additional physical degrees of freedom, which basically make the problem, again, compared to the Wheeler-Feynman case, into an initial value problem. So what you get by introducing electromagnetic fields from a Wheeler-Feynman perspective is Cauchy data. You have, once again, an initial value problem. What you also get is divergences, right? Because now you have the self-interaction problem of the electron, right? And it's the same problem, in fact, that we encounter even in modern quantum field theory. It just gets a different name. There's called the ultraviolet divergence, but it's really the same self-interaction divergence which arises from this duality of particles and fields, basically. So this is a bit speculative, but I think one has a strong case to make that this attachment to this Newtonian paradigm and the insistence on Cauchy data and initial value problems is actually not the root of all evil, but the root of great evil in modern physics, because it actually leads to these sort of divergencies that otherwise you wouldn't have. But, sorry, I know I'm running late. Now back to my simple talk, my modest toy model. One other technical problem with not having Cauchy data is that these models, we say, are not statistically transparent. So it's not so clear how to analyze them, because you do not have a well-defined notion of a state space, or at least not an obvious notion of a state space, on which you could implement a statistical hypothesis or define a measure of typicality. So more concretely, in my case, since this initial condition, the S0, the initial spin configuration, in some cases doesn't uniquely determine the measurement outcome, right? This statistical hypothesis that I have, the equidistribution of this S0, doesn't determine uniquely the outcome statistics, right? Which is an interesting problem. In more technical words, I cannot readily implement A and B, the measurement outcomes, as random variables on the state space, so to speak. But this is all a derivative of this underdetermination of the time evolution by initial data. So the idea here, and it's relatively exciting that this works in this toy model, is to determine upper and lower bounds for the probability of these anti-coincidences. So rather, so to speak, than looking at this initial spin configuration as sufficient conditions to produce an outcome, I regard them as necessary conditions to produce an outcome. And so, given A and B, the maximum probability is the probability assuming that this anti-coincidence, right, the opposite spin, the opposite outcomes, occurs whenever that's compatible with the initial data. Or, in other words, that the self-fulfilling prophecies always favor A not equal B. And the minimal possible probability is the probability I get when I assume that A not equal B occurs only if the other alternative is impossible, right? So this is the minimum possible probability, or in other words, that the self-fulfilling prophecies, whatever it is, in addition to this initial data that in nature that determines the outcome of my experiment, always favors A equals B. So but other than that, those are actual probabilities in the sense of relative frequencies. Just that I cannot make a precise and accurate prediction, but just give upper and lower bounds. And to make things even easier, you remember I had this three parameters, alpha, beta, gamma. Just for the purposes of illustration, I will reduce that to a single parameter. So actually, alpha, beta, gamma are just two independent parameters because their sum is always 1. But now I will estimate that because gamma, so to speak, the strength of this reinforcement, and this is only an echo, right, of the feedforward, that beta that gamma equals beta squared. So now I get a parameterization in terms of one single affine parameter that just parameterizes the strength, so to speak, of the advanced effects. Right, and this is the single parameter beta now. And here I have for different values of beta, so as beta gets stronger, right, the effects of the advanced interaction get stronger. And here I have the probabilities for the anti-coincidences, where the orientation of the measurement apparatus is in this angle of 120 degrees. Okay, here is the maximum possible probability, and here's the minimal possible probability. So we readily see that the effect of the advanced interactions is to lower the probability of these anti-coincidences. Okay, so this is just the prediction of the local model, where this term was 1/3. This is the prediction of quantum mechanics for this case, which is actually 1/4, and this is the range of possible relative frequencies that I get for my toy model, depending on the strength of the advanced interactions is parametrized by beta. And it may or may not be, I mean, the model is very primitive, and I made many simplifying assumptions, so it may or may not be interesting that in a relative reasonable range of beta, it's actually relatively close to the quantum mechanical prediction for this specific case, right, for these specific angles. Oh, yes, sorry. So we see that the effect of the advanced interactions to lower the probabilities actually leading to a violation of Bell's inequality. And here I've plotted, just to show that there's no shady business going on, you can actually plot them by varying these parameters independently. So yeah, the idea is, of course, so it's interesting to note how this model actually manages to violate Bell's inequality, because it has to violate one of the conditions. And here is again the locality condition, so the correlations between A and B has to be screened off by giving all the relevant data in the past. And if you condition here the probabilities just on S0, so just, so to speak, on the initial hidden variable, the locality condition is violated. So in this sense, you would say that the model violates parameter independence. But of course, if nature was really described on fundamental scales by time-symmetric interaction, this would leave out half of the story. So if you also admit here common causes in the future, so to speak, then the probabilities here trivially split, right? Because now here this lambda already contains the information about the actual measurement results. So now the locality condition is formally satisfied, but there's no conspiracy condition is violated. But there is actually nothing conspiratorial about this model, because what you saw of these effects, they did neither infringe upon the freedom to choose these parameters as you like, or have the choice completely random, nor did they affect the preparation state of the system, right? So while the model from this time-symmetric perspective violates the no conspiracy condition, there's not actually a conspiracy going on in the sense that Bell and others deemed unacceptable, right? Because there is, in other words, no correlation between the parameters associated with the preparation of the system and the parameters associated with the measurement. Yeah, and I guess I'm out of time. Yeah, so thank you very much.